Now coming to the continuing with the group 15 elements only, we will see all the elements of this group show positive oxidation state of +3 and +5. The elements of group 15 combine directly or indirectly with oxygen to form a number of oxides. Alright, the important oxides I've discussed with you earlier also. Once more I am saying you the important oxides formed by the elements of group 15. In terms of nitrogen, it is nitrous oxide, nitric oxide, dinitrogen trioxide, that is N2O3, nitrogen dioxide NO2, dinitrogen tetroxide N2O4, dinitrogen pentaoxide N2O5. So several oxides of nitrogen we are having. Similarly, we are having also several oxides of phosphorus, that is P4O6 phosphorus trioxide, P4O8 phosphorus tetroxide, P4O10 phosphorus pentaoxide. Similarly, we have got oxides of arsenic, As4O6 arsenic trioxide, As2O5 arsenic pentaoxide, Sb also same thing, Sb4O6 antimony trioxide, Sb2O4 diantimony tetroxide, Sb2O5 antimony pentaoxide, and lastly for bismuth we have got bismuth trioxide, Bi2O3 and Bi2O5 bismuth pentaoxide. Fine. So in this way what we find is that is on moving down the group, you can see it on the screen, on moving down the group the stability of the group 5 oxidation state decreases. Alright, the group 5 oxidation state, the stability is decreasing. So that is your N2O5, P4O10, S2O5, Sb2O5 and Bi2O5. If you see, the stability is decreasing. From nitrogen to bismuth, the stability decreases. Alright, now while the stability of the +3 oxidation state increases due to inert pair effect. The +3 oxidation state means N2O3, P4O6, AS4O6, Sb4O6, Bi2O3, the stability what you find is that increases in +3 oxidation state. The stability increases. Thus, +5 oxidation state of bismuth is less stable than +5 oxidation state of what you can say antimony, that is Sb. What I said, +5 oxidation state of bismuth. In +5 oxidation state you get Bi2O5 and in antimony you get Sb2O5. So what is being said here? That Bi2O5 is less stable in nature than Sb2O5. We can say that. The only stable compound of bismuth having +5 oxidation state is BiF5. We can say that. BiF5 with halogens, I mean to say here. With halogens, the only stable compound of bismuth having +5 oxidation state with halogens is BiF5. However, it may be pointed out here that nitrogen, because of its small size and high electronegativity and strong tendency to form p-pi multiple bonds, shows all the oxidation state of -3 to +5. Just now I said that all the oxidation state it shows of -3 to +5. That is your N2O, NO, N2O3, N2O5, N2O4, then N2O5, everything it shows from -3 to +5 due to the presence of p-pi multiple bonds. We can say that. Clear? So in this way you can see that it forms several, that is oxides, it forms several fluorides, it forms several oxides also due to the different oxidation state ranging from +1 to +5, so to say. Now if you see that nitrogen does not possess d orbitals in its valence shell. This is a very important point I am discussing with you. Nitrogen does not possess d orbital in its valence shell, because if you write the electronic configuration it will be atomic number 7, 1:2:2p3. Therefore it can show a maximum covalency of 4, and that too when it donates its lone pair of electrons, then it will show 4, that is NH4 plus R4N plus, when it will donate lone pair. Alright, you have read it in organic also. Alright, that is when it is going to donate its lone pair, then it is going to form ammonium radical, then it is form that is tetramine, we can say that it is going to form, that is this tetramine, rather it forms benzene diazonium salt, it forms. Okay, so if you remove R with the aryl group, in other words, nitrogen cannot extend its covalency beyond 4. It is not possible. That is why nitrogen does not form NF5 or NCl5. The question comes here, why nitrogen does not form NF5 or NCl5? The answer is very simple, that it does not possess any electrons, any vacant d orbitals. Alright, it does not possess any vacant d orbitals, so that the electrons can jump from the p subshell to the d subshell or from the s subshell to the p subshell, and hence we can so it can show a maximum covalency of 5. That is not possible in case of nitrogen. It does not show for that particular purpose. Now here you can see the preparation of phosphine I have given you. I am going to discuss the phosphine preparation later on with you, along with some diagrams and all those things. Just now, for the time being, I am saying you that when magnesium nitride reacts with hot water, it gives you, that is, ammonia. But when calcium phosphide reacts with hot water, it gives you phosphine. Mind it. Got it? So you can see the difference also here, that how do we get ammonia and how do we get phosphine. Both are group 15 elements, nitrogen and phosphorus. But when magnesium nitride reacts with hot water, when hot water is trickled over magnesium nitride, it gives ammonia. But when hot water is trickled over calcium phosphide, it gives phosphine. Similarly, when magnesium, that is bismuth, we can say that Mg3BBI2. So it reacts with HCl, you get that is BiH3, you get it. Got it? So that is bismuth hydride, we get it. Clear? Similarly, PCl3, when it is reduced, we get PH3, that is phosphine. So the thermal stability of the trihydrides means NH3, PH3, BiH3, then PH3, all these are trihydrides, we can say that. Our group 15 elements decreases as we move from NH3 to BiH3. Thus, ammonia is the most stable. Now, why it decreases? The reason is the electronegativity decreases. Alright. Thus, ammonia is the most stable. The stability of PH3, SH3 and SBH3 decreases progressively, while BiH3 is the least stable in nature. Yeah, it is occurring at the bottom of the group. So, it is so unstable that it has a half-life of only 20 minutes at ordinary temperature. Half-life. Half-life means, what do you mean by half-life? Half-life means the time for the decomposition of half of the element. That is called as a half-life period. The time for decomposition of the 50% of the element, half of the element. That is called as a half-life. So 50% decomposes within 20 minutes, we can say that. So hence you can understand that how much unstable the compound it is. Alright, how much unstable it is, the compound is. Similarly, the reducing character of the hydrides, the group 15 elements increases in this particular order. I have discussed with you about the reducing character. That is NH3, then PH3, then ASH3, then SBH3, then BH3. It's the reducing character of the hydrides increases. Alright, it does not decrease, it increases. Mind it. Alright, because ammonia is the most basic in nature and BiH3 is the least basic in nature. So if it is least basic means it is most acidic. So all the hydrides of group 15 elements possess a lone pair of electrons on the central atom, and thus we can say that all the hydrides of group 15 elements possess a lone pair of electrons on the central atom and thus behaves as Lewis bases. Alright. Now why group 15 elements? They are known as Lewis bases basically because they possess a lone pair of electrons. They have got an electron donor group present in it. Lewis base, what is the definition? That is a compound or an element which has got a which is a pair of electron donor. That's called as a Lewis base. So nitrogen here, nitrogen, phosphorus, arsenic, antimony, bismuth, all they possess one lone pair of electrons present in it, in its central atom. When it forms a compound, when it forms a compound like NH3, PH3, BH3, SBH3, so it possesses a lone pair of electrons, and that lone pair of electrons can be used for donation purposes. It can be used for what you can say giving to other elements or compounds, we can say that. So hence it forms a Lewis base. Now acidic strength of oxides of nitrogen increases in this particular order, that is N2O, then NO, N2O3, N2O4, N2O5, N2O, NO are however what you can say N2O and NO are however neutral in nature. N2O, that is nitrous oxide, and nitric oxide are however they are neutral, we can say that they are neutral in nature. But the acidic strength of the oxides of nitrogen, it increases in this particular order, that is N2O, then NO, then N2O3 and N2O5. The reason is that the oxidation number increases. As the oxidation number increases, the acidic strength also increases. You can count it and see, you can calculate it and see the oxidation number, you will be getting it. From N2O to N2O5, you find the oxidation number is increasing, so the acidic strength also increases, we can say that. But N2 and NO are however neutral in nature. The acidic strength of trioxide follows the order N2O3 is greater than P4O6 is greater than AS5O6 greater than SB4O6. In fact, AS4O6 and SB4O6 are amphoteric. means they are both acidic as well as basic, while Bi2O3 is basic in nature. Now noted this, children, these are the very important points. These points are very important, that which is amphoteric, which is basic, which is acidic, because the exceptional question comes in the exams. Acidic strength of pentoxide follows the order. N2O5 is more acidic, then P4O10 is more acidic, then S4O10 is more acidic than SB4O10. The reason is that is N2O5 is more electronegative in nature. Got it? It's more electronegative in nature. So hence, due to this reason, it absorbs a pair of electron from the H atom, due to which it is more acidic in nature. Due to which it is more acidic. As I said you, N2O5, it is more electronegative, nitrogen is more electronegative, so it absorbs, alright, a pair of electron from hydrogen ion rather, I should say, very easily, and hence it is more acidic in nature, so to say. Now if you see, I have given you a chart here. You can see it there, the different that is nitrous oxide, the structure I have shown you, and this is the colorless. Nitric oxide, the structure I have shown you, and it is a colorless gas, colorless liquid and solid when pure. Dinitrogen trioxide. Rather, here you can see in this particular chart, I have shown you the structure as well as the characteristics in short of that particular substance. Dinitrogen trioxide N2O3, you can see the structure. You practice all these structures, and it's a blue solid. NO2, it is what you can say, bent structure, it is a brown gas. Dinitrogen tetroxide N2O4, again you can see the structure there, it is a colorless liquid. Dinitrogen pentoxide, it's a structure there, colorless ionic solid. And nitrogen trioxide, it is a radical, it's an unstable radical, you can see it there. So hence this chart is very important to what you can say, distinguish between the different oxides of nitrogen, we can say that, and their structure. The structure is very important, rather I should say, as well as the short description which I have given to you. Got it? Regarding this, now this I have talked with you, that is about the phosphorus, that is the compound of phosphorus. You can see the compound of phosphorus, you can see it there, phosphorus pentoxide, trioxide, and all the structures I am showing you here. How many lone pair it's having, what is the structure it is having, that is the phosphorus trioxide, that is P4O6, phosphorus pentoxide, P4O10. Alright, so the different structures I have shown you there, the structure of the different oxides of phosphorus, rather I should say you. Got it? After showing the oxides of nitrogen, you can see the oxides of phosphorus, we can see that. So next is you can see the acids of the oxo acids of phosphorus and how it is being prepared. The different oxo acids of phosphorus like H3PO2, whose oxidation state is +1, and how it is prepared when phosphorus reacts with water in presence of phosphorus reacts with hot water, it gives you phosphine and H3PO2. Similarly, orthophosphorus acid, when P4O6 reacts with water to give you H3PO3. Hypophosphorus acid, you just write these equations and practice it. When phosphorus reacts with oxygen in presence of water, is give you H4P2O6, hypophosphorus acid. Orthophosphoric acid, H3PO4, when P4O10 reacts with water, it gives you H3PO4. Pyrophosphoric acid, when H3PO3 decomposes to give you the pyrophosphoric acid, so to say. So these are the different preparations of the oxo acids of phosphorus, we can say that. And these are the structure of the what you can say oxo acids of phosphorus. It's very, very important. First you see the preparation, then you see the structure, and you need to practice all the structures. You need to draw the structures, and you need to practice all the structures in your notebook. Remember it. So this you have to do it. Now all the elements of group 15 form trihalides. You know that it forms trihalides of the general form like say EX3, like ammonia trihalides, NCl3 is there, NF3 is there. Trihalides have pyramidal structures, definitely, like ammonia, which is pyramidal. Trihalides are also pyramidal in nature. There the central atom is sp3 hybridized, that is a nitrogen atom. These trihalides are predominantly covalent with the ionic character increasing down the group. Down the group, when you come from nitrogen to bismuth, the ionic character increases. In case of trihalides like NCl3, then PCl3, then you can say ACl3, SbCl3, BiCl3. If you come down the group, then it's what you find is that they are trihalides are predominantly covalent, while the ionic character increases when you are coming down the group. Thus BiF3, here fluoride structure is taken. I was talking to you about the chloride structure. So if you take the fluoride structure, BiF3 is predominantly ionic, while other halides of bismuth, that is BiCl3, BiBi3, etc., and SbF3 are partly covalent, that is partially covalent, and partly it is ionic. We can say that. Moreover, I should say it is polar in nature. The less stability of NCl3, NBr3 and Ni3 is because of the weakness of NX bond. How it is NS bond is weaker? Because the bond, if you compare the nitrogen atom with chlorine, bromine and iodine, so when you go down the group, the halogens, the atomic size of halogen increases, isn't it? So when the atomic size will increase, so the bond length with nitrogen with that particular halogen also increases, and the bond becomes weaker and weaker. Alright, what I said? If you see that fluorine, chlorine, bromine, iodine, when you come down the group, the atomic size increases. So when these atoms, fluorine, chlorine, bromine, iodine, is attached to nitrogen, what you find is that the atomic size also increases, the bond length also increases, and hence the bond gets weaker and weaker. So in this way, you can see it here that how NCl3 reacts with water to form NH3, PCl3 also reacts with water to form not PH3, rather it forms H3PO3, an acid it forms. Got it? So see the difference there. The difference comes in the exam basically, so that when NCl3 reacts with water, what you get it, and PCl3 reacts with water, what you get it, and why do you get it. Got it? So you can see the differences. So hence I have given you this particular equations. That is, when it reacts with water, it forms ammonia, a basic substance. But PCl3 reacts with water, it forms a phosphoric acid. Why? Because phosphorus is less basic in nature than nitrogen. Got it? Less basic in nature. The basic character decreases. Rather, just now I told you the acidic character increases when you come down the group, isn't it? So this you can see the preparation of what you can say, that is PCl3. I'm showing you here in this particular structure that how PCl3 is being prepared, how phosphorus chloride is being prepared here. I'm showing you that particular one here. So just you see the diagram, I'll just discuss with you. Now PCl3 or PCl5, what we do is that we take white phosphorus, and as you can see, dry chlorine is being passed. So when dry chlorine is being passed through white phosphorus, PCl3 gas is being produced, and that gas is being collected in the round bottom flask, and tap water is falling from above. Why? Because PCl3 is a gas, it is allowed to cool down and it forms a solid. Alright, it is forming a solid there, PCl3, we can say that. Clear? It may be also be prepared by passing what you can say, SOCl2 gas over phosphorus. SOCl2 gas, that is thionyl chloride over phosphorus, that is white phosphorus. If you pass thionyl chloride, then also you will be getting PCl3 plus SO2 plus S2Cl2. What I said? P4 plus SOCl2 will give you PCl3 plus SO2 plus S2Cl2, that is sulfur monochloride. We can say that. Clear? It's a red colored liquid, S2Cl2, sulfur monochloride. It's a red colored liquid you'll be getting it. But I don't want now here this particular one. We want that is your nothing but PCl3. So PCl3 is being prepared in this particular manner. Got it? By using sulfuryl chloride also it can be done. That is P4 when reacts with SO2Cl2, it gives PCl5. Then PCl5 further will give you, that is PCl3. We can say that. Clear? In this way you can prepare, that is nothing but a PCl3. You can prepare in the same manner PCl5 also. Now what is the use of anhydrous calcium chloride? In the figure you can see, in the picture you can see anhydrous calcium chloride is taken, which absorbs the moisture which is being present there. Alright, in the tube whatever the moisture is being present, that is being absorbed by absorbed by anhydrous calcium chloride, and it keeps the phosphorus trichloride, and if at all some phosphorus pentachloride is also being formed, it keeps it dry, free from any moisture. We can say that. Clear? Free from any moisture, it prevents, because chlorine reacts with phosphorus trichloride to form also solid phosphorus pentachloride. It may also form along with PCl3. Some amount of PCl5 can also be formed, we can say that. And pure phosphorus pentachloride or trichloride is almost colorless solid, but the impure sample is usually greenish yellow color, which has a pungent odor. Got it? The impure means it will contain more amount of chlorine, so it will be having pungent odor, and it will be having a greenish yellow color, we can say that. Clear. And phosphorus trichloride is a what you can say, it's a colorless mobile liquid. Same thing, it has got a pungent smell, it reacts readily with water and therefore it forms fumes, we can say that. That is PCl3 plus water. Just now I was saying you, it is not going to form pH3, it is going to form H3PO4. Alright, it is going to form H3PO4, PCl3. Similarly, when PCl3 further reacts with chlorine, I said you just now, it formed PCl5, and PCl3 reacts with oxygen to form POCl3, phosphorus oxychloride it forms. Alright, so in this way, so the pentahalides are thermally less stable than trihalides due to inert pair effect, we know that. And all the pentahalides act as Lewis acids due to the presence of vacant d orbitals. PF5 does not undergo hydrolysis since PF bond is stronger than PO bond, so hence it is not easily broken down. Alright, PF5 does not undergo hydrolysis because PF bond is stronger than PO bond, so it is not easily broken down, so it does not undergo hydrolysis. Alright, then coming to the anomalous behavior of nitrogen, that we'll see in the next part. We are going to see the anomalous behavior of nitrogen. But one more thing I need to discuss with you, one more thing I feel that I should say you about it is that is nothing but the preparation of the red phosphorus, that how it is being prepared. How do we prepare the red phosphorus, that I should say you. So red phosphorus, it is being heated. It is prepared by heating white phosphorus at 525 Kelvin. You can see in the figure, that is in the diagram, you can see that white phosphorus is taken. It is being heated at an inert atmosphere for several hours. For several hours it is being heated, white phosphorus. At a temperature of around 525 Kelvin, we can say that we get red phosphorus. So what we do is that yellow phosphorus is taken in a egg-shaped cast iron. You can see it, it's an egg-shaped cast iron retort. It's a cast iron retort, we can see, which is egg-shaped in the figure, which is provided with two jackets for thermometers. We can see that, yeah, two thermometers you can see, and the screen, and an upright pipe with a safety valve and a feeder at the top. You can see everything what I am speaking to you, you see the figure, you'll get it everything in the figure itself. So that is, we are having a safety valve, an upright pipe with a safety valve and a feeder at the top. We are feeding the raw materials there from it. A small amount of iodine is also added. Iodine accelerates the transformation of white phosphorus into red phosphorus. Very important, note this point. Iodine is being added there. What is the use of iodine there? It accelerates the transformation of white phosphorus into red phosphorus, catalyst. That is coal gas or carbon dioxide. Example, the air present in the retort is basically an inert gas, which is coal gas or carbon dioxide. The retort is heated in a furnace. You can see it there. During heating, the care is taken that the temperature does not exceed 525 Kelvin. Why? Because it may convert into another allotrope of phosphorus instead of red phosphorus. You'll be getting it. That is, so the safety valve prevents the pressure from rising beyond a certain limit. We can say that. After heating for the required time, the retort is allowed to cool. Red phosphorus is obtained as a hard mass. It is powdered and boiled with caustic soda solution to dissolve any residual white phosphorus present. Red phosphorus remains undissolved. It is thoroughly washed with water and dried. If you see the red phosphorus as a polymeric structure, it consists of chains. I have showed you. You can see once again here that it's a polymeric structure. You can see the red phosphorus. That is, it is nothing but it's a chain like structure. It is P4 tetrahedra linked together. You can see it there in the figure on your screen. You can see it is because this polymeric structure that red phosphorus is less reactive than white phosphorus. Rather, white phosphorus on the screen also you can see it is not forming a polymeric structure. It is in unique, just one particular structure it is. But red phosphorus, it forms a chain like structure, polymeric structure. So hence it is less reactive than white phosphorus. Understood? The white phosphorus is more reactive than red phosphorus because it is a one particular structure, means it is a monomeric structure. We can say that monomeric tetrahedral structure. But red phosphorus is a polymeric tetrahedral structure. We can say that. Clear? So in this way you can get it. What you can say, the red phosphorus you can prepare it. So red phosphorus basically it is insoluble in water as well as in carbon disulfide. It is odorless and non-poisonous in nature. It's a red solid. It is more stable and chemically less reactive as compared to white phosphorus. In fact, it is stable modification of elemental phosphorus at room temperature. It does not react with caustic soda. It changes into a white phosphorus when it is heated in inert atmosphere and vapors are condensed. Got it? So this is about your the preparation of red phosphorus. I need to say you about it. Then I said you. Got it? The different allotropic form of phosphorus we have earlier we have studied white, yellow, white or yellow phosphorus, then red phosphorus, then black phosphorus. That is it is there. Got it? When white phosphorus is poisonous, understood? It is poisonous in nature. Persons working with phosphorus suffer from fuzzy jaw, a disease in which jaw bones decay. Fuzzy jaw, in which the jaw bones decay. It is a very dangerous disease. Got it? The person, those who are working in the phosphorus factories. Got it? The glowing of phosphorus in dark is an example of phenomena of that is chemiluminescence. Got it? It is an example of chemiluminescence, the glowing of phosphorus in the dark. Got it? White phosphorus. All these are the properties of white phosphorus I'm saying you. Got it? White or yellow phosphorus. So this is all about children about this particular AV. Thank you very much.